And then we are starting to have struggles of keeping the engine running because your operating conditions actually lend themselves to it. And the cooler it is, the more likely you're not taking a huge carbon and chopping it off down to a tiny carbons. You're ending up with intermediates. And the intermediates in the tars begin this process that eventually crack your engine.
Okay. I guess if we could, you had the...
I was actually going to kind of show what gasification is, oddly enough,
okay.
using a match. So I was actually going to... So whenever we have a match, we have wood. Right? Wood has basically two polymers, cellulose, which is nothing more than glucose, sugar, and lignin, which is a phenolic, which is actually a hydrocarbon in aromatic form. And then we have a lot of different things that we can extract, like the most common one is the group of compounds we combine and store as turpentine. Turpentine it's actually the third major component of wood. And so, obviating the fact that we need an ignition source, when we start burning, if you actually, hopefully I don't burn my fingers, you can actually see two different temperatures. Quite clearly, one, it produces a blue flame. I am burning already. A blue flame, the other one is the normal orange. Okay. That indicates two completely different chemical reactions that are actually here. Okay. So, the first one, I'm probably going to hold it out. The first one is, this is kind of nice. Okay, so whenever you burn a match, you will see at the leading end of the flame a drop of liquid. Okay, and that's kind of you can actually tell. Okay, but that's kind of an important telltale sign of the actual chemical reaction that's going on. I am about to burn. The first chemical reaction where the blue color happens to be. The first chemical reaction where the blue color happens to be, it's a chemical reaction that we actually term pyrolysis. Okay, and pyrolysis is basically thermal, just heat degradation in the absence of oxygen. Now you may be wondering, wait a minute, we're breathing, right? So there is oxygen in the room. Well, there is also a lot of energy here. And so the energy around the flame actually pushes the atmosphere we're currently breathing out, allowing for the center, exactly where the blue color is, to be without any oxygen at all. And so in the absence of oxygen, what happens is those huge molecules that are basically the original wood, right, start cleaving, start breaking themselves down into smaller intermediates. Now, it's not the carbon monoxide, but that stage is basically, well, it's tars and bigger. Okay, so they're larger molecules. And when I kind of pointed out that you see a drop form at the trailing edge, those are the end products. It's an actual liquid. And that liquid, I have the reactors there. Anyway, it's called bio-oil, and it's a petroleum-like product. It's black, gunky, it's full of goodies as far as hydrocarbons are concerned. But those guys, obviously, in my reactors, actually collect jugs of them. In a match, you don't collect a jug, right? What happens is, in your match, those liquid products, which, again, when the trailing edge, those liquid products, because they're in a highly energetic environment, just become volatile again. And then you have the yellow, right? And so after you pass the pyrolysis, which is the blue, you have the yellow. Sorry, I already burned myself. And in that yellow, there's still a lot of energy, but it's not enough to maintain the atmosphere we're currently breathing out completely. And so in that yellow portion, there's actually two temperature zones, which I don't know if we're going to be able to see them in the match. But anyway, if we would put actually, there is a black, almost translucent, and then above that, there's a yellow tip. Okay? Yeah. The black translucent is super hot. I mean, we're talking almost 2,000 plus Fahrenheit, where that little black tip was. And you guys can see it there. Okay, so you see almost a colorless portion. Below is blue, above is yellow. And in that colorless portion, gasification is actually taking place. So what happens in gasification is we take those intermediate portions of pyrolysis, and under extreme luck, actually controlled environments, we put enough oxygen in there to break them down into the really, really small compounds. And those small compounds have a super high heating content on it. The top yellow that we see is actually the end product, CO2 and water. Okay. That's actually normal combustion. So, you know, we've all been taught in the school at some point that this is called combustion, right? You put it in. Hey, isn't it good? You put it in and all of this is combustion. In reality, there's 3 different processes, chemical processes taking place. So you see the tip of the dark spot, okay? So there's only limited oxygen taking the chemical reaction to CO2 and water, which happens on the yellow. So when you combine all of those 3 reactions, you have a match. But when you devise equipment to maximize one of those 3 reactions, well, you have obviously combustion, you have pyrolysis, and you have gasification.
Okay.
And so the machines that I have in my lab basically do all. But the gasifier is essentially designed to maximize that band, that dark band chemical reaction, which means that just like the match, it doesn't need a motor. I don't need an external heat source per se. The sacrifice of basically some of the biomass that I'm gasifying with a little bit of oxygen is enough fuel to sustain the reaction. But trying to find that balance between the exact amount of oxidant, that is of air, that you're allowed to go through, so that you get exactly that band and not pyrolysis and not combustion, is really where kind of the trick is. And depending on your biomass stream, you do have to invest some time actually fiddling in order to get the trick correct.
We were talking earlier about the updraft, downdraft,
yes,
and invert.
Yes.
Just if you could brief explanation on that.
Sure. Or do you want me to actually show you?
I guess we could probably just do a quick explanation here and then show the.
It is. It's based on how the gases flow. So let me. All right, let me see if I can use this. So, okay. It's almost like a gasifier, by the way. The main issue with it is that in a downdraft gasifier, gases go from the top down.
Okay.
That basically means your oxygen, your atmosphere oxygen, basically what fuels that little black band, has to be controlled in such a way that at the bottom, which is where your biomass is and where your heat source is, you only feed enough of the oxidant to maintain this chemical reaction.
Okay.
So the gases exit here already being mostly small, ideal, right? And then you collect that elsewhere. You have air, basically heat zone, air, biomass, heat zone, in that order, okay?
Okay.
Downdraft and invert. The invert reactor, essentially it's not an open top reactor. Basically has a sealed top on it, and you feed the oxidant through tubes. Okay. That are closer to where the gasification chamber actually is. Okay. And so it's actually a quite effective way of pre-treating. So you walk in already with heat or heated air rather than getting really cold air, which Alaska normally have. So anyway, those are the 2 main differences, and for the updraft, it's the other way around. However, the order of the things doesn't change. So what happens? You have basically your heat right at the bottom here. On top of that, you have your biomass. And while in downdraft, we had to go through air, had to go through biomass and then heat. In updraft, it goes heat and then biomass.
Okay.
Well, what happens there is that you're not pushing those big gases through the heat zone, which is what happens in the invert and the downdraft. Rather, you're pushing the gases out. And I'll show you the gasifiers. You have actually stages, really tall stages, where you take the exit gas from. That is kind of the Achilles heel of the system, because depending on things like moisture and the original composition, you may actually end up with a reactor that's over 10 feet tall, which is fine. The advantage of one versus the other is that in the updraft, because you're basically taking pyrolysis volatile compounds out rather than gasification compounds out, you can use dirtier material. You can use things with higher moisture content, because you're not really looking for the really tiny compounds. You're happy with, you know, a mix of fairly big combustible cars. But that being the end product, it means that the heating content and essentially the utility, using that for internal combustion engine,
that's gonna gunk it up pretty bad.
Yeah. However, on the flip side, for the downdraft, you do have to control moisture big time, because it is essentially biomass underneath the heat source, and then the gas is going through. And so, if your biomass is really, really moist, well, guess what's going to go first? It's going to go water, right? And you're pushing it through your heat source. What are you going to do? You're going to quench it. So your reaction basically disappears, it stops. And so you have to be kind of cognizant of the practical application of them and what your biomass is in order to choose which system better suit whatever it is you're trying to do. For research purposes, which is all the purpose I have, they both serve a very strong kind of case. But I clearly don't design my experiments based on kind of a universal feeling that I'm going to get the same products using both types of reactors. I know that's not going to be the case. So, in kind of big picture, that's sort of the differences between the three type of reactors. You have commercially actually fluidized bed, which I don't have here, but it's a chamber with sand or some other solid, and you force pressurized gases, small amount of oxygen. It's really important to have that there. And the entire sand or whatever solid material we have in there is, along with a reactor, taken to the temperature of gasification, which ideally happens above 800 degrees centigrade.
Okay. Pretty hot.
Oh yeah, very hot. And for the water phase shift reaction, we want to be way above 1,000.
Oh, wow.
Really hot.
Yeah.
But again, you're able to actually have a more homogeneous mix with fluidized beds. And so the entire, I wish I could show you, but anyway, the entire column, which is filled with sand or generally sand, it is basically motion. It's in suspension.
Okay.
And so you can shove in biomass in there by simple compaction with these extremely hot grains, right? Sorry. You have a very good thermal exchange, and so the materials gasify.
So you're saying with the sand, it's motion. So is it basically saying the gas going into the sand, it's suspended in between the individual particles?
The biomass.
The biomass is okay.
The gas is exiting.
Exiting. Okay. Okay.
So the guts of both the updraft, downdraft, and invert are basically the same design. They're a double barrel system. And I don't know if your camera is going to be able to catch this, but essentially you have an inner barrel that has a comb. That comb is actually where kind of the magic where it happens.
Okay.
It is designed so that it fits inside another barrel. Your is this area right here. It has many different configurations. I can show you the different types of configurations. This is where the highest degree of heat is concentrated. And because there is a second barrel basically here, it kind of keeps it in place.
Okay.
The invert design is what these coils are. So they feed into...
Oh, the feed tubes that you were talking about. Okay.
Feed tubes which are in the center. You can bring your camera and look at them. You can see them from... Actually, you may need to see them from here. Probably can see the little hoses.
Yeah, I see them right in there.
Okay, so where my hand is kind of the highest concentration of heat.
Okay.
And you want to insulate, all of the gaps.
Okay.
And, you know, the idea is so you actually maximize the amount of thermal mass in one specific area. And so above it, you can actually feed the biomass. And because in this particular design, in the downdraft design, we actually have air going through that biomass.
Okay.
You then push through the temperature gradient, you push the chemical reactions to break the biomass down. The exit is actually going through that. The gases actually exit outside of here, and they get channeled, as you can see, through a cherry. And they are driven by fans, and the fans are fans. Nothing particularly about it. Motorized fans that control, because this basically is connected through the outer shell. This fan basically creates a vortex. It sucks up the air, which is mostly a gasification product. And so controlling the speed of the fan controls the amount of air that actually goes through the heat exchanger.
So you have just a little bit more control over the feed.
If you put too much speed on the fan, you're putting too much oxygen through. You're not gasifying. You put too little, you actually don't push enough mass through.
Okay.
You are technically gasifying, but you're not able to actually make use of gas.
Oh, okay.
And so when people try to drive cars, this is not needed. You just put directly your throttle body, put directly to this guy. The more you accelerate, the more vacuum it creates, and the more gas it
Sucks something.
But the main key of the whole thing is you have a correct venturi. There's another gas car. You need to have a separating device, venturi or something along those lines, that will be able to remove as much tar as we can from the system. But again, that's a big challenge. In my particular case, I've devised actually a cooling chamber to drop the temperature really, really cold in order to actually try to get those liquids to run out. And what they are, and these are different types of, these are from normal wood. As you can see, there's kind of a translucent mix. And these guys, again, are just from the chicken pellet type of by the store. They're not even my own make. And there's plenty of liquid in there. So again, we're looking, this is, let's see, we ran probably 2 or 3 kilograms of biomass, which runs about 45 minutes.
Okay.
And this is how much liquid we got.
Wow.
45 minutes. Again, think of your engine.
Okay.
That's an issue.
And doing an hour road trip is going to be quite a bit of gunk buildup.
These are the type of parts that you can expect. These are already done. But basically this type of composite is...
Okay. Not good.
Yeah, and again, these are very small, but again, some of my experiments, I've done a whole bunch of different types of biomass.
I don't know if you can actually